Hey, so I wanted to put together this video to show you guys some steps that I would use to calculate the inductance of a coil and the capacitance of a capacitor that I was making. In my case, it's usually on a flex PCB using the copper on the PCB, but you can use a really similar plan for when you're hand winding a coil and putting together a capacitor with some kind of copper foil tape or something like that. So to start out, I wrote out a document detailing what I'm about to explain that we're just going to go through, but the location of that document, it's called Coil and Capacitor Calculations. It is in the shared folder you all made called the quad card, and I put a folder in here that contains all the things I'm adding called RFID design Corey. So you click in here and then you click on calculations, and I have a couple pieces of information and then this document in there, coil and capacitor calculations. So navigate to here and follow along if you want to try this out. So to begin, before you begin any calculations, you need to know a rough approximation of how big the coil you plan to make is. When you're doing this wound by hand, there's going to be a lot of wiggle room and tolerance on these values. So you're basically just trying to get into a ballpark and then, add or remove turns or slightly change the size and iterate the design a few times until you get it right where you want it. And once you have it where you want it, you can then measure the dimensions and the resonant peak and, like if you want, measure the inductance and the capacitance directly with a meter and try and verify those real world values against your calculated values, and that'll allow you to adjust your calculations in the future with like a tolerance. So for this coil, just as an example, I'm going to be using the rough dimensions of the ID1 card. So I laid out an ID1 card, which is like what a credit card form factor is, in Eagle. You don't have to use Eagle. I'm just using it because it's really easy for me to make the dimensions on here. But I did that so that I could calculate the size of things. So an ID1 credit card is 85.6 millimeters long and 53.98 millimeters tall. Or wide, but we're not going to have the coil be exactly as wide as the card because then the edges would get damaged. So I'm going to say we'll just use, for this example, I'm going to use a 3 millimeter isolation from the edge for our coil. And this is the outer edges of the coil. So every additional turn of the coil will be moving further inward from this rectangle. I hope you can see my cursor. I checked to make sure it was recording correctly, but I don't think I checked to see if the cursor was visible. But so if you add that 3 millimeters of isolation, it would create a coil area, like the outer edges, that are 48 millimeters wide by 79.6 millimeters long. So we're going to use those values. I wrote them down here. And for that's for the outer coil. For the inner coil, which is the one that's going to couple with the COM module, we're going to do 9.62 by 9.23 millimeters is the size of the COM module. You can find that online. I put a picture in here in the shared drive, which details some of those dimensions, but they actually come from a document called ISO 7816, and that's for all these credit cards, integrated circuit cards. And then the specific one that has the information on the contact interface is number 2. I actually have that. Unfortunately, I can't share it with you guys, but it details the dimensions for like how far away from the edge of the card the contact interface needs to be, and the minimum area of the actual contacts. but I verified that against this picture and it's accurate, so you can just use this. So we have the size of our outer coil and the size of our inner coil. So to calculate an inductance for a coil of that size, we can use an online calculator. I personally use one that I included here in the zip file. That's based on some calculations I got from a application note from a manufacturer called NXP, and they make like chips like this. But the online calculators, I verified them against that calculator, and they're pretty close, so it doesn't really matter. I'm just going to use this online calculator for ease. So we can click on this, and it pulls up this calculator page. And so for the calculator, it's talking about a rectangular antenna that's flat, and it only is talking about having it on one side. In our application, I think that we're only going to have an antenna on one side. I have done designs where there was antennas on the top, there were antenna windings on the top and bottom of the PCB that aligned with each other, and it's not a linear relationship. It's very difficult to map out how much inductance you're going to get if you add coils on the bottom too. So for now, we're just going to mess with having one coil on the top of the PCB with a set number of turns. Or, I mean, in your case, it would be one coil that is wire in a set size and just one layer of wire. You have to enter the length and the width. So in our case, we already have those. It's 79.6 millimeters long and 48 millimeters wide. So you mentioned in a call recently that you were going to use you were going to use 30 AWG magnet wire. And I looked that up, and that means that the diameter of the magnet wire is 0.254 millimeters. And so you can put that as the track width. Obviously, the tracks on a PCB are rectangular, and you're talking about a cylinder-shaped wire. So it's going to be a little bit off, but it's okay. It'll be pretty close. And for the track gap, hypothetically you could put 0, but there is a thickness of the enamel on yours, so I'm going to say let's put 0.1 just to be safe. That's probably a little big, but we'll take it. So the width of the copper is 0.254, and we're going to say the width of the gap between each winding of copper is 0.1. In this case, they're talking about the height of the rectangular track on a PCB, but if we want, we can just make it more accurate by making it the same as the diameter of the wire. This means that we're going to be cutting off the corners because this is treating it as a rectangle. So the area of the copper, like the cross-sectional area of the copper, is actually going to be even greater if we do it this way. But it'll be okay. The error will work in our favor because it will actually increase the proposed inductance that it's going to calculate. And then I mention here that for most NFC antenna designs, which this 13.56 megahertz antenna is operating very similarly to an NFC antenna, which is what your phone uses. That's why your phone can talk to it. It's the same frequency, and the protocol is very similar. So for those, they recommend like 2 to 5 turns. So I'm going to say we'll start out with around 3 turns that go around the entire perimeter of this card, and we can work up or down from there. So I will put the number of turns 3. We don't have to worry about the fitting parameter right now. That would be like for if you had an error propagation that you wanted to add. Making this number larger up to 1.85 will increase the proposed inductance. I actually don't know why they're adding this. I looked it up, and the document is also from that company NXP, and they don't describe what this even is. So we'll just leave it at the default value, 1.65. But once you have a reasonable approximation of what your antenna is going to look like entered into the calculator and hit calculate, it is going to give you the inductance. So in this case, none of these numbers are actually going to mean anything. Like they're below the noise threshold. So we're just going to go with our inductance is 1.43 microhenries. So I'll write this down here. Proposed inductance of outer coil is 1.43 microhenries. So that's what that mu, it's this engineering notation. It's you do like for millimeters, you like milli and all that, you know, like micro, nano, pico. So 1.43 microhenries. That's the unit of inductance. So now that we have our outer coil, a proposed inductance for it, we're going to do our inner coil. So our inner coil is much smaller. It's 9.62 by 9.23. So like 3 turns of that size is going to be like a minuscule inductance. It's going to be like tens of nanohenries, maybe 100 nanohenries, which is like 100 or 1,000 times less than a microhenry. So we're probably going to increase the number of turns on that one to, let's say 5 is a good place to start for this, so that we get good coupling with the comm module, which has many turns. We've seen pictures of them, but for a coil module, this would be an example. This one has 12 or 11 turns on it. So we're going to need a significant number of turns to couple well with that. So let's start with 5. We don't want to crazy overdo it for the first tests. So especially because I think it's very easy to overshoot the inductance, and it's very easy to overshoot the capacitance, but it's much easier to overshoot the capacitance. Like a little tiny bit extra area is going to give you like 100 extra picofarads of capacitance, which is going to completely throw the whole thing off. So for your first attempts, to make your life easier, try and undershoot the inductance a bit to give you more headroom for when you inevitably don't have a great time with the capacitance. So we're talking 5 turns, and the outer dimensions are 9.62 by 9.23. So let me add those. Same track width and track spacing. The number of turns we're going to do is going to be 5, and it's going to say that the inductance here is 0.2, and I'm going to round, so 0.24 microhenries. Okay, so that's our proposed inductance for the outer and inner coil. Now, remember that in this design, for each comm module, so for now we're just trying for one comm module, just to see if we can get it working. Eventually, I talked about in the last video, we might do 2 comm modules and kind of like work the antenna windings in amongst each other, which is going to be much more complicated to math out, and we're going to have to do more trial and error. But for now, let's just do one comm module because the behavior is going to be much more predictable. But remember that for this design, the outer coil and the inner coil are going to be connected to each other in series. And then both of those will be in series with the capacitor if you decide to use the capacitive plate. So when you connect inductors in series, they're just like resistors. You can add them up. If you were to connect 2 inductors in series that are like, right next to each other, it's not going to work that way. They're going to actually dramatically change the inductance by being in proximity to each other. But the outer coil and the inner coil are far enough apart. They're going to be like, we saw here, this would be the inner coil on the left side here, and then this larger rectangle is the outer coil. There's a pretty good distance there. It's like 7-something millimeters, so they can be treated as separate coils. So because they're separate, we can just add them together. So our proposed total inductance would be 1.67, which is just them added together. Okay, so if we were to do that, we now have good inductance. And that's actually a little low because I only did 3 turns and 5 turns. I mentioned here, oh, this is wrong. I mentioned here that a lot of times they attempt to have these inductors like around 2 microhenries. So that's for a normal NFC antenna where you want it to be evenly weighted in the inductive and capacitive ends to get good performance. Because if you add too much capacitance, then the range of frequencies that the card operates at will be very wide. So it'll read under bad conditions, but the amount of power that it's going to receive, like the peak on the VNA, is going to be very short. So it's not going to be able to communicate very well with a reader, which when you're doing payment transactions, there's cryptography involved and it's very energy intensive. So you want a good balance in most cases. But in our case, we may actually want to weight the circuit more towards the inductance side and have a very small capacitance. So we could go all the way up to 8 microhenries, possibly. We'll have to do testing. But if we weight the circuit higher in the inductive end, then there'll be very little capacitance on the plates. And when you introduce your finger to the circuit, you will introduce the tiny amount of capacitance you add, like maybe 10 picofarads, is going to make a huge difference because there's only a tiny bit of capacitance in the circuit. So that will allow us to do that very careful tuning so that when your finger is not present, it won't read, and when your finger is present, it will read. So we'll have to do testing on that. But for now, we're going to stick in the 1.67 microhenries range. I find that the values that you experience when you test the circuit are usually much higher than the calculated ones. Maybe not much higher, but like a few percentage points higher. So, having it be such a low value is actually okay. But we can now move on to the capacitance, the capacitor calculations. But there's one thing that you should always check first. Because if you just calculate out an inductor value and assume that your inductor is going to be that value, you're probably wrong. You're off by some amount. You're never going to be perfectly right. So the best thing to do is make that inductor like we proposed with those dimensions, and then solder a known capacitance to it. Like say, I don't know, you can get like a 47 picofarad capacitor pretty easily. They're very common. Something like that, like in the between 10 and 100 picofarads. Solder that to your circuit and then test it with a VNA and see where the resonant peak is. If you have a known capacitance, because you plugged in the capacitor, and a known resonant peak, then you can use a calculator like this one I linked right here. Plug in the 2 known values, 47 picofarad, and this one's got to be megahertz. If we know our resonant frequency, say it's like 15 megahertz, we plug in those 2 values, we can calculate what the inductance of the coil must be, and we can compare that inductance to our calculated values to figure out what our error was. And then we'll have a pretty solid value for inductance. It might be a little bit off because the inductor itself, like the windings in the inductor, in between these, they're at different voltages. Like this one's at a lower voltage than this one, which is a lower voltage than this one. Because resistors, the voltage drops across them in series. So as you travel through this wire, which is a resistor, more and more of the voltage, like relative to this point, over here is like 20% of the voltage. Over here is like 60% of the voltage as you travel through. So because of that, there's a little bit of capacitance called parasitic capacitance between the windings. So this value is not going to be exactly accurate. You're probably going to have to add a little bit, like 8 picofarads for the coil, just because of that parasitic capacitance. So you could say like, oh, this is way off from my calculated value, but actually I'm just going to guesstimate and say that there's 55 picofarads because of the parasitics. Oh, that's much closer to my calculated value, you know. So you can try stuff out. Don't assume that any calculations are going to be right. No, because it's very wibbly wobbly. There's a lot of tolerance on everything. But yeah, once you have a rough idea of what your actual real inductance was compared to your calculated inductance, you can move on to figuring out how big your capacitive plates need to be. You can, I would recommend you aim for a target frequency of about 14 megahertz, even though the real target is 13.56, because a lot of things are going to add capacitance and inductance to your circuit, and every time you add capacitance or inductance, it makes the resonant peak go down in frequency. So we want to aim a little high because it's always going to be lower than we expect, you know? And don't expect to have a functioning circuit on your first try. You're going to need to do a little bit of tweaking based on real values the second try, you know? So if we wanted to have a target capacitance, so we're aiming for 14 megahertz. Let's open up this resonant frequency calculator, get rid of the capacitance because that's the value we're interested in. Add 14 megahertz as our target frequency, and add 1.67 as our inductance. Like say we tested it, it was actually 1.67. So if I add that, I want a 77 picofarad capacitor out of those plates that we're making. And that's picofarads. So like milli, micro, nano, and then this would be like 100. That would be 100 picofarads. So very little amount of collected charge or charge storage capacity. So that's our values we have now. So we need to figure out a way to make a capacitor that is 77 picofarads out of some copper tape. So this is the equation that you would use. There are calculators online, but they're missing a lot of critical elements. They don't handle the permittivity very well. So there's a permittivity, which is the capability of a medium, like air or something like that, to support the propagation of electric fields. Because what we're doing here is we're putting a metal plate and then a separator, which is a dielectric material, and then another metal plate. So that permittivity of that separator is how difficult or easy it is for the electric fields to propagate through it, and for like the material itself to be like charged positively and negatively on one side versus the other. So there's a permittivity value that's for free space, like vacuum, and it's really important to use this value times the relative permeability or permittivity in your calculations. A lot of times you'll see just type in the relative permittivity and it'll try and do a calculation, and it's not always accurate. So I usually do the calculations manually. I'll use a tool like Wolfram Alpha just because it makes it easier to enter the equations and do like a more complex algebraic thing like this. Rather than, like, you never trust yourself to do it by hand. So, but you need the permittivity of free space. You need the relative permittivity of the material you're working with. So in this case, for the flex PCBs, it's polyamide film, and its relative permeability is like between 3.3 and like 3.5. So we're going to go 3.4. You can need to pick an area of the plates. So like for ease of use, I can just say 1 centimeter squared of this copper foil, and then I have to convert it to meters squared for the calculation. And then you need whatever the distance is between those plates. So for the polyamide flex on the flex PCBs that PCBWay makes, and for like a lot of other polyamide you'll find in the environment, it's often a thickness of 0.025 millimeters or 25 micrometers. But for some really thin designs, like maybe if we're doing a 0.1 millimeter thick PCB, it would be 0.012 millimeters. That's about as thin as it goes, though. Yeah, so an example I used here, you're talking about using copper foil tape. I looked on 3M, the manufacturer's website, for copper foil tape, and a lot of those were like EMI shielding. So they're like a copper foil with like a conductive adhesive on both sides. They're not really two plates separated by a separator. So they're not really ideal for emulating this behavior. I recommend you attempt to get some Pyrolux, that's what they call it, this stuff. Copper clad laminate. That's not actually a picture here. So I can show you what Pyrolux looks like. It is a polyamide film, and then on both sides they'll plate it with copper. So this is literally what flex PCBs are made of, oftentimes. It's this pile of polyamide film with the copper laminate on both sides, and then they acid etch off the laminate in the areas where, or the copper in the areas where they don't want it, and make a flex PCB. So you can just get the raw plates or the sheets of Pyrolux. And I picked a very specific one, this LF7014R. I have the data sheet here. You can go to it, but I'm just going to pull it up. So the 7014R has a kapton thickness of 25 micrometers. So that's the one I was talking about earlier, and it has a copper thickness of 0.5 ounces per foot squared. That matches up with, I can go to PCBWay's website here and go to their Flex PCB page and look at the specifications that are available for the Flex PCB. And if I pick a 2-layer, 0.1 millimeter thick FPC thickness, so 2 layers, 0.1 millimeters thick, the only option available to allow that thin stack up is the 0.5 millimeter, 0.5 ounce per foot copper. So to match up with the behavior that we expect from the Flex PCB, we're going to aim for this Pyrolux film that has properties very similar to what they're going to use in the Flex PCB. So given those material properties, we've got our vacuum permittivity, a rough estimate of the relative permittivity. It's tough that we're not going to be exact. Like this needs to be pretty exact, and the distance between the plates needs to be pretty exact for us to get an accurate value, which is why we're never going to be able to estimate accurately what our capacitance is going to be. We're going to have to measure it. But we want to get close, so we're going to use these values. And I did an example calculation here with a 1 centimeter squared plate. So if I formatted this, with the parentheses and everything, this section right here could literally be pasted into Wolfram Alpha, and you would get a result, and that result is listed down here. So it's 1.2 times 10 to the negative 10th. If you were to type all that out and count, make it milli, micro, nano, pico, you would get 120 picofarads of capacitance. So an example of doing the calculation the other way around would be you just reorganize this algebraically so that, here is listed up here, so that the area is on the left side and the capacitance is in here somewhere, and you enter the capacitance value you need. So in our case, it's 77. Rearrange this and get A equals whatever, these other values plugged in maths out to, and that'll give you how much area of copper you need to cut out in order to get that capacitance. Yeah, sorry if that was a little confusing. There's a lot going on, and I'm open for further questions. I just wanted to provide this as like a primer to walk you through, because just textual instructions are kind of confusing. But yeah, so for your first design, try it with the coil, the hand-wound coil, on some kind of adhesive material. Attach a known capacitance to it. Measure the resonant peak to figure out the true inductance. Plan out your capacitance around that inductance so that it will resonate at the target frequency. And then try and make a capacitive plate that is similar in capacitance to that. And when you get through that whole process at the end, the only unknown will be, you'll have a reasonable confidence in the inductance, plus or minus like 5-10%. The only unknown will be the capacitance, because, this seems like you could perfectly math it out, but you just can't, because you can't cut it perfectly, and the thickness of the carrier material, the polyamide, is not 100% consistent, and we don't know the exact permittivity of a specific sample of polyamide. So there's a good amount of wiggle room there. So you're just going to have to figure out what you think the capacitance will be based on your good estimate of a known inductance and the resonant peak, which you can measure directly with a VNA. Yeah, cool. Well, let me know if you have any more questions, and we can go over this in the next meeting if you made some attempts and it didn't work out the way you expected.